ionic, but does it have really strong or really weak intermolecular forces, attractions to other molecules? Strong. That's why that it's a solid. That's why it's staying all together like this. What about water? What's happening to it?
Melting.
It's melting. It's going through a phase change, and that phase change is it's melting. So if I compare that to the salt, the attraction of those water molecules to other things, keeping it really rigid, is that very strong? No. Now, if you don't know dry ice, I like to bring it in just because I feel like you can't leave high school chemistry without actually seeing this stuff. Do you guys know what is dry ice made out of?
CO2.
It's CO2. Breathe out. That's what it is. Is your breath. Is it melting? Is it turning into a liquid in front of you? Check it out with my shirt here. Okay. What's it turning into? A gas. We've got a vocab word for what it's doing. Sublimating or sublimation or going, it's subliming. That's the way to say that.
Can you not hold it with your own?
It's really cold. You just can't hold it in like one spot for a long period of time. Alright, yeah, so I'm gonna do that. Okay, so what I want you to picture is we've got carbon dioxide. Right now it is stuck together in a solid here, but do you see how those carbon dioxide molecules are leaving very easily? Does it have really strong or really weak intermolecular forces?
Really weak.
Super weak. It's got a weak attraction to other carbon dioxide molecules, so it's not staying stuck together as nicely as the sodium chloride is. Which one falls in the middle, just on the spectrum for us? Water does. It is attracted, just not as strongly as the sodium chloride molecules are. I'm going to set this guy right back down here. So we're going to use this idea of this attraction between these molecules and what makes things stick together and how well they stick together to kind of explain to us the differences between solids, liquids, and gases. Second grade, I know this is what my daughter's doing right now in the class, which is, I think, when you guys first started talking about it. I have a little simulation. In your notes, we'll wrap this up. Solid, liquid, gases. With the person next to you, I want you to describe these. What's the same between them? What's different between them?
They all.
Molecule flavor.
Oh.
Hybrid.
Yeah. I know what you mean. I'm pretty sure the word for that though. Hard. No, I know what you mean. So like condensed, and so they're like packaged some molecules really quickly. Set the word.
Or we can say gas.
Yeah.
We don't know how to we might need to do that. All right.
Yeah.
Physical, you know, it's the
All right, so right up front, I have the solid state, I guess, just kind of pictured for neon that's here. And I think something that's magical, if you take your hand and put it on your desk, remember we talked about how you're not really touching it? Okay. I also want you to be aware that it is moving. It is moving. Does it feel like it's moving? Oh, okay. Wait, what? No. It doesn't, again, these things that we're talking about are so tiny. But I want you to picture, up here I've got solid neon pictured. Is it moving? Yes. These atoms, these molecules, even if they appear to not even be moving, they are. How are these atoms moving?
Together.
Yeah, the movement that we say that they have is they have vibrational movement, I guess. How are they packed together? Yeah, they're packed, I'm just gonna say they're packed neatly together, okay? Is there a lot of open space? Yeah, there's not a lot of open space. Solids, does it have a definite shape? Or is the shape changing? Okay, they have a definite shape. Which means does it have a definite volume? Yes. Okay. Can I compress this?
It's a gas.
Okay, for a solid.
Yeah.
Okay, a little bit. We say that it's relatively incompressible. We can just a little bit. Do you guys know what I mean by compressing?
Yeah.
Okay. I'm just gonna say relatively incompressible. If I were to take, I've got up here food coloring. Wait. Here it is. Okay, I've got my solid sodium chloride up here. And I put it on there. Do solids diffuse? And what do I mean by that? Yeah, what is diffusion? Yeah, George.
When molecules from different areas try to balance out.
Yeah, try to reach, call that equilibrium, George. I would write yeah, equilibrium, where it's kind of like they evenly like mixed together is I think the thing might be a better way to say that. I do want to mention, you guys, there is reading associated with today, and I will do it. Let's take this. Let's compare this to the liquid. Describe it, compare it to the solid, the person next to you.
There we go. Less than.
Yeah, what is less definite?
Yeah.
And then what definite?
Yeah. Yeah. I think it would use.
Look at that one up there. Like, ouch.
That's exciting, look at it go. Alright, how are liquids moving if we compared it to the solid?
But
Yeah, we still have some vibrational movement. What else do they have? Yeah, they're not packed neatly. So I'm going to add one more piece onto this movement. We have what is called translational, which means that these atoms, which can I spell movement? Hold on, movement. These atoms are able to move past each other. They're able to go up, they're able to go down and slide around each other. That's what translational movements, forwards, backwards, to the left, to the right. That is, I can't write movement apparently. Okay. They are not packed as neatly. Do they have a definite shape?
no.
Do they have a definite volume? Yes. Yes. Me too. Which one of these will take the shape of the container that it's in? The liquid will. So if you put water in a bowl, it's going to take the shape of that bowl, which is what we mean by no definite shape to it. Looking at this, you guys, is there a little bit more space between these atoms? Can we compress them? Better than the solid. Yes, this is actually how hydraulics work. It works on the compression of different liquids. We'll say that they are compressible. If I took water and I added some food coloring to it, will it diffuse?
Yeah.
Yes. Why? They're moving faster, they're translating back and forth, which is allowing that mixing of that food coloring in with the water. So I'm gonna write that they diffuse. What's happening here with these atoms? One's escaping. What do we call that? It's escaping. Is this substance boiling? No, what's happening to it? If you picture, I've got water sitting up here. This is happening. Every now and then a water molecule is leaving. It's evaporating. Every now and then an atom needs enough energy to leave, to break. What force is making these stick together? Intermolecular forces. That's what's making these stick together in that liquid phase. And every now and then one of those atoms gets enough energy to break that intermolecular force. We call it evaporation. Guys, let's compare this to the gas. Are they vibrating? I'm going to say that these have translational. Okay. Are they packed neatly? Are they packed at all? No. So what's in between all of these atoms? Space. So they are not packed. I'm just going to write there's empty space. There's empty space between them. Does this have a definite shape? I'm going to say no definite shape. Does it have a definite volume? Okay, what determines its volume? The container now is what determines the volume this is taking up. I'm going to say there's no definite volume. And I'm also going to write that volume is determined by container. Okay. So if you put a gas in a really big container, it will occupy that space that's in there. Can it compress a gas? Yeah, look at, there's all this empty space in there, so if I applied some sort of pressure and made that container smaller, we can compress it and make those atoms closer together. So they are compressible. Stole my daughter's perfume. If I sprayed perfume, is that perfume going to diffuse in this room? I'm not gonna do it, so I hate going into like Macy's or Nordstrom's in the perfume department. So these diffuse. Which one diffuses faster, a liquid or a gas? Why is that?
That moves way faster.
Yeah, they're moving faster. Which one of these, let's say I had a solid, a liquid, and a gas at room temperature, which one essentially has no intermolecular forces?
Gas.
Gases do. Which one has really strong intermolecular forces? Solids do, that make them pack together. So this is why, you guys, last unit when we talked about how 1 mole of any gas takes up 22.4 liters at STP, that is for all gases, because we assume all gases have really no attraction between those atoms that are there. And this is why we've got a special kind of set of chemistry topics that we can bring up just based off of these gases that are here. I am gonna stop here today. Tomorrow we're going to talk about these gases, how we change these phases between them, a solid, liquid, and a gas, and how gases exert